Welcome to the Chapter 6 Part 1 video. We'll be looking at radicals, specifically finding nth roots and nth roots of nth powers. We're going to start with a little bit of vocabulary. A radical is the symbol that we use to draw roots. So, for example, a square root would be a radical with no number above the front of the radical. We don't have to write a number there because that is our default radical. We also have things like cube roots or fourth roots, which we started talking about in class. So for an nth root, the index or the number in front of the radical is n. The radicand is the number inside of the radical. So when we're looking at a radical, the number inside is the radicand. Okay, if there's a number in front, we would call it the coefficient. And then we would have the coefficient times radicand under the radical. So only the number underneath the radical is called the radicand. And then the number that indicates what root we're taking is the index. So we have the radical, the index, and the radicand. And then if, there isn't always, but if there's a number in front, that would be the coefficient. And those are some terms that we will be using throughout this chapter regarding radicals. So to find nth powers and nth roots, what we need to understand is what it means to find a root. We talked about this in class. When we're finding a root, we're looking for multiples of the same number that are factors within a number. So we're factoring to have the same number as the factor multiple times. So what does that mean? Well, 3 to the first power means 3 times just itself one time. 3 to the second is 3 times 3, which is 9. 3 cubed is 27. 3 times itself 4 times is 81. 3 to the fifth is 243. And 3 to the sixth is 729. Okay, so we're multiplying a number times itself that many times. -3 to the first, again, -3 times itself one time will just be itself, -3. But if I have -3 times -3, notice that becomes a +9. This is one of the patterns that we talked about from the spreadsheet activity that we did. Then we have -3 times -3, so that's 9, times another -3. Now that's going to make a -27. -3 to the fourth, 4 is even, so that's going to be a +81. -3 to the fifth, 5 is odd, that makes a -243. -3 to the sixth, 6 is even, so that's a +729. Notice the pattern of alternating positive and negative. And then we have things such as our roots, okay? So let's look at our roots of positive numbers, our radical with an index of 1. So this is the first root of 3. Now, when we're saying a first root, that's kind of like raising something to the first power. It's just going to be itself. So both for positive and -3, the first root is just itself. The second root means I need two numbers that multiply together to get 9, two of the same number that multiplies together to get 9. Now we know that 3 times 3 is 9, but we also just showed that -3 times -3 is 9. So we actually have two answers here. For 27, to get a +27, only 3 times itself 3 times. 3 cubed gave us 27. For 81, now we got 81 from both the positive and -3. So we have two answers for that one again. Then for the fifth root of 243, for the fifth root of 243, only 3 to the fifth gave us 243. So that will be just 3. For the sixth root of 729, there are actually two possible numbers that give us the sixth root of 279. So that's plus or minus 3. Now, if we look at the next column over, our next blank to fill in is the square root of -9. Now, we've actually seen this before. We can look at this as the square root of -1 and the square root of 9, but we know that the square root of -1 is not real. So this is not real. If we're looking at non-real numbers, if we're including our complex non-real or our imaginary numbers, then we can say that the square root of -9 is 3i. But if we're looking for real roots, they should never have I. Real is a type of number, right? Real roots never have an I. So this means there are no real roots for the square root of -9. Cube root of -27, we know that -3 times -3 times -3 gave us -27. So the cube root of -27 is -3. The fourth root, this is a typo, it should just be 4. The fourth root of -81, again, we have a negative. There's not a negative number that when I multiply it 4 times will give me 81. So -81 is not a real root. The fifth root of -243, we saw that the fifth root of -243 is -3. And then we have the sixth root of -729. 6 is even, and we have a negative. There are no real roots. So the pattern here is just like before when we were raising our negative numbers to powers, we alternated positive and negative. When we take the radical or the root of negative numbers, we alternate negative and not real. So the values that would have had a positive exponent or a positive solution when we raise it to an exponent now have no real solution when we're looking at radicals. And the reason we don't have a solution is because that -3 actually gives us, -3 squared gives us a positive radicand. Okay, so let's see if we can summarize this here. In the table we saw, if I have a positive base to an exponent, this gave us a positive value. If I have a negative base to an exponent, that alternated positive and negative. Okay, if I have a radical with an index with a positive base, this gave us a couple cases. We have if the index is odd or even, and then we have if the base is positive or negative. Okay, now if the index is odd, so this is something like the cube root of 8. Okay, the cube root of 8 will be positive 2 in this case. If the index is even, let's say the square root of a positive number such as 4, we saw that there's actually 2 ways to multiply a number times itself to get 4, and that is both the positive and negative. So 2 squared, but also the quantity of -2 squared. 2 squared and also -2 squared give me 4. Even though there are 2 roots to the question of the square root of 4, I will specify which one I'm asking for by calling the positive one, we'll call it the principal root, meaning the main root. So if I'm just asking for the square root of 4, I only need the positive one. If I want the negative one, I will ask for negative square root of 4. So even though there are two different numbers that give us the square root of 4, in general, if I'm just asking the square root of 4, we'll ask for the positive one. We saw the square root principle in our last chapter. This is why the square root principle exists. There are actually two numbers whose square is 4. But if I'm asking for the square root of 4, you only need to give me the principal or the positive one. Okay, now if our index is odd, so let's say the cube root of a negative number, let's choose negative 8 because it's a perfect cube, then my answer here will be negative. And then if it's even, if I have the square root of, let's say, negative 4, this is not real. No real solution here. Okay, so we have 4 cases when we're looking at radicals. We have to check both the index and the radicand. Okay, so it's summarized here in this box here. If a to the n is b, and a and b are real numbers, and n is a positive number, remember when we had a negative exponent, we got fractions. So what this is saying is that it's not a fraction. Then a is the nth root of b. Okay, if n is odd, then we just get the number back. So when our index is odd, we're happy because those are the easiest one. If the index is odd, we don't have to think too hard about it. There will always be just one solution. Okay, if the index is even, then we get into the more complicated cases. If the index is even, if the radicand is positive, we'll have 2 answers. If the radicand is negative, we'll have no answers. Okay, so if it's even and positive, that's 2 answers. If it's even and negative, that's no answers. Okay, so that's 2 different ways that we can kind of show you what is the pattern when we're taking the nth root. Okay, so let's take a look at some examples. So we want to find here in the example the cube root of, so I'm going to write this, the cube root of 0.008. So the question is, what numbers multiply to 0.008? So I'm going to say 0.008. Well, I know, let's first deal with the decimal. This is 1, 2, 3 decimal places. So that's 1 over 1,000 times 8. So 1 over 1,000 I can actually write as 1/10 times 1/10 times 1/10. And 8 is 2 times 2 times 2. So the cube root here is going to be 1/10 times 2. 1/10 I have 3 copies of, 2 I have 3 copies of. So our answer here is 2/10 or 0.2. That's how we can apply it to a decimal. What if I have the cube root of negative 1,000? Well, we have negative 1,000, which is negative 1 times 1,000. And 1,000 is 10 times 10 times 10. So I know I have a factor of 10, but what about that negative 1? Well, I can write negative 1 as negative 1 times negative 1 times negative 1. So that I have 3 copies, and that is how our cube root of negative 1,000 is negative 10. And then we have the cube root of 1 over 27. 1 over 27, I can write that as 1 over 3 times 1 over 3 times 1 over 3. 3 times 3 is 9, times 3 again is 27. So our answer here is 1/3. Okay, what if we do the 4th roots? I'm going to do it in a different color. Now I want the 4th root of 1. Well, any root of 1, I can write 1 as a multiple of itself as many times as I want. So the 4th root of 1 is 1. Any root of 1 will be itself, will be 1. How about the fourth root now of negative 0.0001? Well, we can do the decimal part like we did before, 0.123 zeros, and then 1 means that that's 1 over 1,000. 1, 2, 3, oh, nope, 10,000. 4 decimal places is 4 zeros. So that means I can write it as 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10. But now I have to deal with that negative, right? So negative 1, I can do negative 1 times negative 1 times negative 1 times negative 1. 4 of those will make it negative. I need another positive, another negative 1 to make it negative. So there's no group of 4 negatives that will give me a negative. So this is left as the fourth root of negative 1, which is not real. So if I have an even index and a negative number, this means no real solution. Okay, and then lastly, the fourth root of 16 over 81. Well, 16 is 4 times 4, or 2 times 2 times 2 times 2. So I can make that a 2 in the numerator to get 16. And then 81 is 9 times 9, or 3 times 3 times 3 times 3. So that's a 3 in the denominator for the 81. I can always double check by actually raising it to the fourth power. 2 over 3 to the fourth power. 2 to the fourth is 16. 3 to the fourth is 81. So it's 2/3. Okay. Box my answers here. I'm going to give you a couple to try, and then after you put in the answers on Edpuzzle, I will show you the solutions. Okay, you can check your answers here. Pause the video while you check your answers, and then I will move on to the next topic. So the next thing I want to take a look at is the nth root of nth powers. Now this is really what we were looking at in the activity that we looked at, because the first thing we did was raise our base to a power, and then we took a root of it. Okay, now the reason we did that is because I wanted our roots to be integer values whenever possible, instead of getting fractions or decimals or radicals in our answers while we were kind of uncovering the patterns for this chapter. So if we're looking at any number A, it can be any real number, okay? We can break it into even or odd numbers, okay? If we have the nth root of A to the n. So what does this mean? This means I take a number to the nth power, I get the answer, and then I take the nth root of it, okay? And every time I do that, I want to say the answer is A. But let's look at an example. What if I take negative 2 squared? That's 4. Okay, and then I take the square root of 4. Well, that's 2 or negative 2, right? So A was negative 2. Our principal root is 2. Now remember, the principal root means if I ask for the square root of 4, you don't have to give me both 2 and negative 2. If I'm looking for negative 2, I will ask you for the negative square root of 4. So principal root is the one that if I take the square root of 4, I'm only asking for the principal root. Okay, so if A was negative 2, then our answer wasn't A, our answer was the absolute value of A. So what does this mean? This means whenever my base is negative, if I take the square root of negative 2 squared, and remember, I don't have to write that 2, I can just write it as the square root of negative 2 squared. This is going to be the absolute value of negative 2, which is 2. How does that change if my base, instead of being negative, is positive? If I take the square root of 4 squared, because this is not negative, I don't have to worry about the absolute value bars, because the absolute value of a positive number will always be positive. Okay? So if I take the absolute value of 4, I should still do that, but because it's positive, the answer will be 4. If I don't know whether the base is positive or negative, if it's a variable, if it's x, let's say, then I have to do it in absolute value bars because I don't know whether x is positive or negative. So if I have the fourth root of x to the fourth, I'm always going to write that as the absolute value of x. The only exception is if I said x is positive, then I can say the fourth root of x to the fourth is just x, because then the absolute value of a positive number will be itself. Okay, what about when our index is odd? So what if I have a cube root of -2 to the third power? Well, -2 to the third power is -8, and the cube root of -8 is -2. Because odd powers keep their negatives, we don't have to worry about the absolute values for that. If I have the cube root of 4 to the third power, that's the cube root of 64, which will be 4. Whatever sign had, the number had, will stay the whole time when I'm working with odd indexes. So just like before when we were looking at our odd indices, the odd indexes are a little bit easier to use. When we're looking at even indices, we have to be careful. If there's a negative in our argument, if I had the fourth root of -16, this is not a real number, right? The reason we can now have negative bases is if I square this, now it is a real number, right? -16 squared is then positive. So we have to watch out, be careful of the rules. And while it doesn't matter if you do the power or the index first, sometimes the index will be easier. We always have to keep in mind, what will the sign be doing when I raise that power? Okay. So let's look at some examples. We have the square root of 16x to the 8th. So the first thing I'm going to do here is I'm going to separate out the numbers from the variables. The square root of 16 and then the square root of x to the 8th. Now the reason I do that is because I know the numbers. I know that the square root of 16 is 4. I don't need an absolute value for that. The square root of x to the 8th, though, I have to be careful with. Okay, so x to the 8th factors into x to the 4th times x to the 4th. I have two of a kind, okay? But I don't know if x is positive or negative. So I should take an absolute value of that. So I should do 4 times the absolute value of x to the 4th. However, x to the 4th, anytime I raise a number to the 4th power, it will always become positive, right? So the absolute value of x to the 4th will always be positive. So even though we don't know if x is positive or negative, we do know that x to the 4th will always be positive. So our answer here is 4x to the 4th power. Okay, let's try the next one. The cube root of a to the 6th, b to the 9th. Cube root makes us happy. We don't have to worry about absolute values because 3 is odd. So I want to know a to the 6th. What do I multiply 3 times to get a to the 6th? Well, I could do a cubed and a cubed, but I need 3 copies, not 2. So I'm going to write 1, 2, 3, 4, 5, 6 a's and make groups of 3. There are 2 groups of 3, so that's a times a. B to the 9th, I can do the same thing. I need groups of 3, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. B to the 3rd. You may have noticed something. Since I'm splitting these into groups of 3, what I'm doing is dividing the exponent. This is 6 divided by 3 is 2. 9 divided into 3 groups will be 3. So what we can do, and this relates back to those fraction exponents, if I think about a to the 6th, b to the 9th, to the 1/3, this is a to the 6/3, b to the 9/3, or a squared b to the 3rd, right? This is kind of a sneak preview. We'll be working more with that fraction exponent later on, but I just wanted, if you're already making those connections, if you're seeing those patterns, I wanted to tell you that those are real patterns. Okay, our last one here, the 4th root of x to the 8th, y to the 12th. I need 4 factors of the same thing for a 4th root. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8 x's into groups of 4. That gives me x squared. And then for the y, I've got 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is y to the 3rd. If I had another y left over, it would stay under the radical, but I didn't. Nothing left over, so that was nice. Okay, so here we have our answers for parts B and C. I'm going to have you do a couple of examples now. Try this, and I will show you the answers after you put them into Edpuzzle. Okay, here we have your solutions. Make sure to check your work, and then when you're ready, resume the video and it will be the lesson check. So for this lesson check, there are 6 questions that I want you to answer. You're going to do them on your notebook and turn them in as a PDF on Blackbaud.